All right, welcome everybody. Good morning. So this morning, the CEO of Figure just released their second generation of their Figure robot. I've got Scott Walter here with us, and we're going to take a look at this new demo. It's a 2-minute video, but he also shares all the different specs. There's quite a bit to run through here. Let's watch the demo first. Nice. I'm going to turn down the music because you never know about the copyright. Why don't you speak over it as we watch it?
Okay, so yeah, it looks a little bit self-aware when it starts to open up here. A couple of the shots are reminiscent of the Figure 1. So as we start to go up here, we'll see that. So we can see the movement of the legs, the arms, everything else, and the hip. So they changed the hip design quite a bit, but we've seen kind of a similar shot from Figure 1 to get an idea of the contrast. And there are some things that may not be apparent right away, but become clear when you look at the technical write-up that they had in there. And that is, it's using an exoskeleton design. So that's why things seem very cylindrical, because they are actually, the skin that's there is actually carrying the load and is there to be able to protect it against balls and everything else. So that's one of the differences. And of course, we can see that the hand looks to be a lot more dexterous than the original one. It's got extra knuckles in there. We're going to get into where those cameras are. The camera placement is very interesting. The other thing is, like, start counting. I see 3, but they talked about a small fleet. We're going to get an idea how big a fleet is. Okay, now we see 4, and then we're going to see a 5th one coming on up here. And so we know that there are at least 5 of these. And if they've been able to produce 5 of them, it means that they've done something for them to be able to build them at a fairly good rate. And again, this is now showing it actually in the line. We'll do a frame-by-frame breakdown of what's going on here, but this is demonstrating actually on the production line at BMW in Spartanburg. And so we can see what Figure 1 was already accomplished earlier, and that is to be able to do the placement and correct its behavior whenever you have something that's not placed quite right. It figures out what are the different ways to be able to solve the problem. So, yeah, the robots are coming. It's getting ready there. There's a lot of little nuances we can go through as we slow everything down. But that is basically the demonstration video that they have. And then, as you said, Brett had an awful lot of additional information with a technical write-up.
He actually asked you. You actually asked him 2 questions: the weight and something else, and he answered it. And so, just like literally a few minutes ago. So
Yes.
this is what his post was this morning, introducing Figure number 2, the world's most advanced AI hardware, exclusive pics, and full technical write-up. So they said that this is a ground-up redesign. 6 cameras. Is that more or less than what you're expecting, Scott?
I think that's about what we would expect.
50% plus batteries.
Yeah.
Did they tell you 20 plus hours, right?
Yes. Now, Herbert, I'm just hearing a little bit of echo in the background. I think I'm hearing myself. Oh, okay. So the 6 cameras is not a surprise, because that's what we're seeing on a lot of the other bots to be able to do that. So that's not quite a surprise. If we look really closely in the video, we'll see that it's got a big Cyclops camera, which is probably the main camera, and it seems to have 2 right around where the shoulders are. So some very small cameras there, and in the back they actually have a suite of 3 cameras in the back, which give you. So stop right there. You see, those are not where fasteners are. You've got 2 cameras that are down low.
So I never noticed the Cyclops thing. Okay, just
yeah. So you got a big camera in the middle.
Yeah,
and you don't have 2. You don't have multiple ones that would give you stereo kind of view. But you've got that one, which is probably a nice wide field, and because it's on a platform, we were able to see for sure that the head is able to move in 2 directions. So it's able to swing back and forth and also be able to nod. And then you have the stable platform down there on the chest, which probably helps give them the stereoscopic view that they want to have.
Oh, I see. Those 2 little tiny cameras.
Yes.
Okay,
Yes.
gotcha. Well, let's go through this. So there's onboard vision language model, 3 CPUs and GPUs, fourth gen hands, although still 16 degrees of freedom, integrated wiring, exoskeleton structure, speech to speech reasoning, and he goes through each one of them. The first, so this is a beautiful shot, of course. It looks great.
Yes,
It's a lot
yes, it is.
slimmer. What do you
And I
think
have to
about the
say that,
shoulder design?
yep, that's kind of getting to the shoulder design that I want to see it, at least by angling it up. So you'll notice that those two actuators are not horizontal. They would have, I think, maybe about a 15-degree cant on there, which is good because that means when your arm is straight out, you're not in the singularity of those three axes. So it's a little bit better for control and everything else. There's two things I guess I didn't quite have on my bingo card, and one was the exoskeleton. So I wasn't expecting that, and Brett explained a little bit the reason for doing that. And the rationale is that figure one was not designed for falling. So you need to have these things robust, especially if you're going to be in an industrial environment. So doing that, made it far more robust. It also makes it a little bit easier to do the internal cabling and harnessing, because now you have a hollowed out structure that makes it easier for you to be able to run that. So that's another huge advantage to being able to do it that way. And again, the whole idea of having an exoskeleton is that you're kind of reducing the overall mass potential for being able to do that. So he mentioned, because I thought, with the exoskeleton, you're going to reduce the mass. But it turned out because of other things that they were doing, they actually increase it. So it's around 70 kilograms total. I wasn't expecting it to be quite that high, but I'm not sure the other bots have been able to come up with making themselves that much lighter either without making some compromises. So one of the things that they've done differently here that was also, let me say, the second surprise was the size of the battery pack. So we got a glimpse of that battery pack on Thursday when they did the announcement of the announcement, or was it Friday? Was when I think we had the actual. So Friday we got the teaser video, and in there we could see in the torso that there was definitely a battery pack in there, that they'd integrated the battery pack in there. And we could sort of count the number of batteries. It was a bit tough. I came up with around 66. And based on that, that would have been about 1 kilowatt hour of battery pack, unless they had a second layer. And I wasn't sure if they were going to stuff a second layer in there, but it looks like they've got a second layer in there because they're like a 2.3 kilowatt hour battery pack as well. And does that number sound familiar to you, Herbert?
No.
2.3 kilowatt hours. Do you know who else has 2.3 kilowatt hours?
I don't. Who is it?
Tesla bot is 2.3 kilowatt hours. About all the other bots out there are probably in the order of 1 kilowatt hour.
Okay.
Now he said 50% more energy than figure one. So that backpack that they had in figure one was had quite a lot of batteries in there, but still not quite that much. So they integrated it in, which means the center of gravity is a lot better. You don't have that big mass in the back that you're having to deal with. It's able to stand up a little bit straighter doing it. But the most important thing is you see that number there, approximately 20 hours of useful work per day.
Yeah.
We've talked about that number. Yeah. Remember? I've done an analysis of that. CERN has done an analysis of how you get to that. And is that a good number? So how do we get to that 20 hours? That's not a 20-hour backpack. So
where do they get their batteries from?
Oh, they probably get it from any supplier. So they're probably like 2170s. So they'd be able to get it from Samsung or LG or CATL, anyone. So I'm not sure where they get them, but they're a standard battery that you can pay. I can get them easily on Amazon. You can just go there and order them, and you'll get shipped within a couple of days. 140 2170s that you can use for any one of your projects. So the supply chain for that will not be that complicated. Actually, it's very easy right now because so many companies are not building EVs. There's a glut of these batteries on the market right now, and it's not consuming that many compared to an automobile. So there's no problem with that. The main thing is, what's the strategy to get 20 hours of useful work out of these bots? And that is to leverage the current break schedule that you already have in your factory schedule.
Right.
Morning breaks, lunch breaks, afternoon breaks, breaks between shifts is more than enough time to top the battery off. So I suspect, again, with that size, you can get maybe 6 to 8 hours of actual work out of it before the battery is dead.
Especially if it can carry human strength. If it has human level strength.
In the worst
20
case,
hours. Great.
In the worst case, it might be that you're getting like 4 hours out of it before it's dead. The thing is, you always have less than 4 hours between any sort of scheduled break. So if you can just make it to a certain break, you can then top it off. That will then get you the next one, the next one, the next one. And then at the end of the day, and there's no such thing as like a real 24-hour shifts within these factories. There's always a little bit of downtime for maintenance and getting ready. There's time between shifts. So they've designed it. They size the battery pack, and that's why we're hearing 2.3 kilowatt hours. They sized it based on the requirements of their customer. When they sat down and did all the math like we did, they realized, 1 kilowatt hour is not going to do it. 1.5 kilowatt hours is not quite enough margins that we're going to need to be able to do it based on the amount of effort and energy that's going into these different tasks. So that tells me that they're focused right now on the factory setting and not at home. Because remember when we talked to Barrett about the 1X bot, he's looking to go straight to the home, to the consumer. And they have a much smaller battery pack. And he says, yeah, everyone says that you only need to get about an hour or 90 minutes out of it before you get a recharge. So there's no need to have an oversized battery pack if you're just looking for small tasks. The factory, no, you don't want the bot to have to recharge every hour. You really want to make sure that you're able to get more out of it.
Okay, let's take a look at the rest of the note that he sent, because he went, section by section. First, he obviously started with speech-to-speech reasoning. So it's capable of speech-to-speech conversations with humans, onboard mics and speakers connected to custom AI models trained in partnership with OpenAI. The default UI to our robot will be speech. So he's got the OpenAI model, common sense reasoning from images. Sure thing. Here's an apple, right? We saw that one. Neural network policies, fast dexterous manipulation, whole body controller, onboard robot images. And each of these can pretty quickly make things happen. So from some sort of speech to actual happening. So you got, can I have something to eat? He immediately speaks or talks back, sure thing, here's an apple. But then there's also behavior. And so I've got the old version of this. Sure thing.
So from that, you can see a lot of the differences.
Yeah.
Obviously, the cable management is much better.
Can you explain why you did what you just did while you pick up this trash?
On it. So I gave you the apple because it's the only edible item I could provide you with from the table.
Great. So based on the scene right now, where do you think the dishes in front of you go next?
Notice the lag
on the table, like that plate and cup.
Yeah, I was saying that is a lag. Are you saying that lag is going to get better because of the new onboard camera, the CPUs? Did they increase the CPU so that lag will now be better?
Well, in this case, it's because it's going to the cloud.
Yeah.
It's the cloud up there. And so from that, it's then that's why you get a little bit of the lag. So if you have something on board, then the thing that's on board is going to make it a little bit quicker. So the latency there will go away. We don't know whether it's still having to go external to solve some of these problems, but John can weigh in here. We just had that discussion. John's had his second cup of coffee. I think he's ready to go.
No, this is just water, unfortunately. I didn't have time for another cup of coffee, so I'm only half caffeinated. So, hey, hi. This feels very weird to jump from one live stream to another. I'm like just hopping live streams. But yeah, the question is the VLM or vision language model that Brett talked about is probably OpenAI's, and that's probably that thing that we saw demoed. Gosh, what was that? I mean, it was 2 months ago now, but we never have gotten access to it, which is that speech-to-speech model. And so they're leveraging, I believe, OpenAI's model to do that. But the question is whether it's doing it on the edge device, in other words, on the humanoid bot, or whether it's doing it remotely on their servers, on OpenAI servers. My guess, and we'll have to wait for, actually, I was just answering questions that the commenters had on my live stream, and a big question was, which one is better, Optimus or Figure? And I said, we're really going to have to wait for some demos. We need to actually see demos to get a better sense of which one is better.
So the CPU and the GPUs were upgraded. Now they're saying it's 3 times the computation and AI inference available on board compared to the first generation. This enables real-world AI tasks to be performed fully autonomously Our AI data engine will provide latest AI models that will run on robot GPU. So this is so
But that does not include the speech-to-speech part. So that's what I was wondering. My guess is that they're still sending that out to OpenAI's servers, and then they're sending back the instructions, and then it's acting on that. That's just a
Okay.
guess. We'll have to wait and see.
Is there any reason why it couldn't be done locally? Are there any that run locally that you're aware of?
Oh yeah, you can. I don't know about speech-to-speech, but you can certainly run
Yeah.
Llama locally.
Yeah,
So
yeah, yeah.
there's two
Llama
reasons.
makes it.
Right. One is technical because it's probably a huge amount of compute power, but the perhaps just as important part is the proprietariness. Is that OpenAI may be like, no, we're not giving.
Okay, let's
giving you the
say
model.
yeah, but let's say they don't say no because
Okay,
we
yeah.
know that you can get Grok with a queue,
Yes.
which allows you to run a large language model locally on
Right.
your own CPU. The thing is, what is the power requirements of that kind of inference? So if you're able to do
Yeah.
speech to speech and you had something that could do it locally, you're talking something that's consuming 25 watts, or you talking about something that's consuming 500 watts?
It could easily be the. 500 is probably on the low end. It probably is
On the low end.
Oh
Okay.
yeah, I mean it's
Okay.
if we're going to have a sophisticated model, it's going to be now. What they could do is they could put their servers inside the building at BMW. so
Yeah,
that
yeah, 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 yeah.
intranet
That's going to
works
say.
very, very
So,
fast. So,
if
yeah.
you can get rid of that latency, because if you're
Yeah,
spending
exactly.
500 watts just on inference or
Yeah.
something like that,
I
forget
think
it.
it's
There's your energy budget right there.
Yeah, I think
That's
it's
it.
substantially more than that actually.
Wow. Okay.
Yeah.
Okay.
I mean that's why they have those giant server clusters there. I mean they're for training, but also for inference. There's a lot
Right.
of.
So I
iron
assume the
that's
inference
going
is small because what's the FSD chip when we're driving? Is that about 100 watts for the inference?
I think the hardware 4 is more like 200 now.
Okay, it's about 200, but that's dealing with that's all the inference, right? That's all the video and everything else, figuring out how to drive and stuff like that. Now you got to get that small because even though you've got a big battery pack in your Tesla, if you're consuming 500 watts or 1,000 watts just on the inference alone,
Right.
then your range is just going to collapse. So
Yeah.
you've got to keep that small. So I was assuming the same thing. So the onboard inference that they have, how much energy do you think it's consuming?
Well, so okay, so there's a whole this actually gets complicated as you start peeling the onions, because the other problem with vision language models or large language models, well, nowadays we've got small ones that are pretty compact, but you also have a memory footprint. These things were not designed to fit on small devices. They were designed to fit in large data centers. So it might be the models might be 100 gigabytes, right? They're just never going to fit on a bot. So, that's just something you can't do. Now, eventually, of course, we will get to this being done on edge devices, but my guess is we're not there yet.
Okay.
So
again, you're gonna have to have basically the Borg queen in the room that everything is kind of tied to. Right. Or if you go back to that, remember the old Star Trek with Harry Mudd, you had
the central android who was
it?
I
always forget his name. It's like Herman or something like that. Yeah. But yeah, he was the one that when you got him to break down, then nothing worked. So it may be that's the same model, is that you really do need that big brain to be able to handle it. Partly because, like you say, just the amount of edge computing you'd have to put in the bot would be prohibitive as far as the size. But the main thing, it's going to kill you on the energy budget.
And again, remember, a car has a 75 kilowatt hour battery pack, so 200 watts continuous is not that big a deal. Although
not that big a deal, but still, it adds up.
Range. Yeah, it adds up.
Yeah,
it adds up. Not nothing.
All right, so Scott, can you and John, can you guys compare head to head? What is the difference between TeslaBot and Figure 2 at this point in terms of every single spec that you've seen here?
Okay, so if we go through it, the degrees of freedom that they have in the hand now is
16, a
little bit better than you have in the current generation on the Gen 2, and it's mainly that they added the an extra knuckle to each hand, to each finger. It's not that they've added any sort of abduction in the movement, so they won't be able to play the piano, but they do have that kind of movement. I suspect they took the sensors out of the hand. They used to have tip sensors, but they don't have them in there because they probably didn't have a need for them. They probably discovered that they don't need them based on the test that they were doing. So that's my suspicion. We can verify that. I didn't mention anything about the hands having sensors built in. So I suspect they're not there because they feel they're not needed.
So do you think they're just using back EMF on the
I think so. I think so. And the original one had it in there, and Brett mentioned that they ran the test and they found out they didn't really need it.
Right.
So now there
okay,
may be some edge cases where you wish you had something like that, but
Right.
probably for what they're looking at, the battery packs are the same size. So that means both of them are basically the largest ones that are out there compared to the other humanoid bots where we have some sort of specs on or where we've done some calculations. Most of them top out somewhere around 1 kilowatt hour versus 2.3.
Right. Although if you look at the torso of the figure bot, it is substantially smaller than Optimus's torso. So they're squeezing it into a smaller package.
Right. Now to do that, I'm trying to think, okay, where the heck's the compute then?
Right.
Because I don't know how they get that in the torso and then get that battery pack in there. So it may be that they actually decided to put it in the head.
Yeah.
Now that main, ideally you don't want to put anything up there because the more mass that you put up in the head, the more balance problem that you have. But those components are probably light compared to everything else.
Yeah.
And so since you need a head up there, you need the cameras, just go ahead and use the volume. You get the volume, try to show.
Although I will say that it's surprising not to see venting up there if there's actual significant energy usage.
Yeah. Considering we see the venting everywhere else. So in the shoulders and in the torso, we see a lot in there. We don't know whether, see, around the neck, you do have the collar around there where it's wearing. So that there's some kind of fabric there. Maybe it's a breathable fabric.
Right.
But it's very clear that there's adequate venting for that.
Okay, wait. So let's just review. The hands, there's a huge difference, right? Because figure 2 has 16 degrees of freedom. Tesla is going to go with 22. And then if you saw the wrist of figure, it's still that empty. It's just really a connection point because the actuators are all in the hand, so it's heavier. They only and so Tesla has already explained that they're going to make the muscles into the forearm.
Yeah.
So
now the thing is if you listen to Elon's words on what he said on Lex's podcast, he said that we're going to have a 22 degree freedom arm, and I thought, wait a minute, was that a slip of the tongue? No, and then he went on, and then he said, basically we're designing a whole new lower arm. It's basically a new arm. It's not a hand. And that makes sense because we always wondered, from not including the elbow, but basically I said, well, that means they're now counting the wrist as part of the hand, whereas you can see in this case they're really decoupled. Figure has an arm plus a hand attached to it. Tesla is going to the entire lower arm is integrated in there, and when you want to get things that really mimic what a human is doing, that is like the best approach when you look at it from, rather than decoupling the problem, actually making the problems integrated in there. It also means that if you're able to move your actuators back here, your palm can be a little bit smaller because now you're not trying to figure out how to get those actuators in there. But still, this is a fairly advanced hand to be able to do the task that they want. It looks like it's fairly robust from the covering that's on there because they're working in an environment where you have a lot of very sharp parts everywhere, a lot of hard parts. And so the wear and tear on this is going to be very difficult handling that sheet metal day in and day out.
Okay. And what about the speed of the walking?
It seems kind of slow to me, but perhaps adequate enough for the task that they're doing. So it looks to be about the same as that of the Tesla bot. Yeah. The other thing is to notice that it still has the bent knees as it's walking.
And it's also totally flat-footed.
And that right now is not actually just a policy problem on walking. It's actually built into the range of motion that they have there. So you can see they can never get the legs perfectly straight. It also seems like they probably have a little bit more work to do as far as being able to do a toe off.
Right.
Because given the design that they've done on the foot, it seems to me they should be able to roll up on the toe and get a little bit more off it.
Herbert, if you go back just a little bit to where that other robot turns around, keep going. You could right there. Look at that. You can see the hips actually that second degree in the back robot, not the front one.
Yes, which is why you have that.
Yeah.
So they've done that to try to increase the turn speed for sure.
Yeah. So that's really cool.
So how fast is that turn speed? Do you like it? Because remember, you kept complaining how slow it is. At least it's a pivot now.
Yes, it's able to do the pivot, so it's a little bit better. And again, it looks like they might be able to improve that a little bit over time, just with the software. That you see, it takes kind of 2 steps to do it. To me, it seems like you should be able to do that almost like in one step and do a little bit quicker.
Right.
So guys, this still looks like that this is in Figure's headquarters. It does not look like
no. So here's what's going on is that this is in Spartanburg, but it's in a prototyping area, which you typically would have for prototyping new things. And so they're bringing in some of the actual features. Now that's right on the line. So what they did is in one area, they were going through and validating how everything was going to work. And now they've brought it down to the real line.
We
So
still
in the
don't
first
know
case-
if this is actual useful work being done in a line currently today. This could still very much be a demo.
It is a demo, because if you go back to the original one, if you back up a little bit, you can see it's in a lab area. That's the production hall. It's definitely a production hall, because you can see all the safety equipment
It could
around
still
there.
be a demo,
Right. But the demo here is that you'll see the way it's picking up the part. It's, how did the part get on to that frame there?
Right.
A human put it on there so the robot could grab it. So right now they are focusing more on getting it into the fixture as opposed to getting it out of the dunnage. So if you pause it right there, you see where those big orange crates are, the dunnage. Typically that's loaded with different components in there. Someone's taking those components out and putting in the frame to make it easier for the robot to be able to pick it up. Normally you want to be able to go over there and just grab out of that bin and bring it over and drop it in. That frame that you see there would not be there in real production. You would have probably another piece of dunnage there. As a matter of fact, they need to have 3 of them around there because there's 3 different parts. And so you need to pick up one from each of them and bring them over to be able to drop them in. So it's still in a prototyping phase. They're still demonstrating it can work, and they're integrating it with the actual safety equipment. So you notice what the bot is doing, and that's why there's cameras in the back behind it.
Right.
Is it's backing out. So it walks backwards, and then when it clears the light curtain, then the curtain can drop, and then the production can start. This also highlights a lot of the changes that may be happening in the future, because a lot of that stuff that's designed around there that's happening is designed around the fact that you have humans that are in there and all the safety considerations that have to go in. So you want to make sure it's easy to load. That's the whole idea, is that you've got those tooling pins there. That basically you just drop something and it almost falls into place. And if it isn't there, you can just, again, with like the back of your hand, just knock it into the right place.
Right.
What you're not seeing there are those fixtures close yet. They close when the curtain comes down, because when the curtain comes down, then it's a lockout situation. There's no human in there. It's now safe for those clamps to come down, because there's not going to be any fingers in the way. And all those things add time to the overall process, which might be fine, because the spot welding robots need about 45 seconds to do their task. So long as you can get the next cycle done within that amount of time. Now, more than likely they have something that spins around, so you keep the spot welding robots going the whole time. So that is on the floor, but then you can see this is where they set that line up, where they brought in the actual tooling fixtures that they use down on the shop floor, but they don't have all the safety equipment. They've kind of mocked it and everything. You don't have the curtain that comes down. You don't have the clamps that are closing, because that's just very complex stuff to be able to duplicate over there for the training purposes. Now they've got it trained, they're going up in there. The next thing I want to see is them being able to pull those things out of an actual bin, because it's easy to come from underneath and get that. But when you're trying to pull it out from under the bin, you've got to separate the 2 pieces of sheet metal. They're there. So you've got to figure out how to get your hand in there. And that's going to be tough on the hands. So they've got to figure some way to be able to get underneath to be able to get the leverage you need to pick up the part and then get the part and bring it on over.
Right.
Now, this is about, the production rate is in the order of a minute. Maybe it's 49 seconds or something like that, but it's not 30 seconds, something like that. So each of those bots has about that amount of time to be able to complete the full cycle. It could be the way the factory is. You see there was 2 stations next to it. You could set that factory up that a human might be able to service both of them at the same time. I don't know enough about everything else that's going on there, but we saw that in the Tesla video in Shanghai, that the operator was like going between the 2 because he had more than enough time to do it. And he was able to do it very easily.
Okay, and you talked to Brett immediately, and you said the only spec missing is the weight. With exoskeleton, it must have lightened up a bit, and walk speed. He replied to you quite quickly. He said, yes, that helped mass, but the exoskeleton. But we increased it on the other end. More battery, more cameras, more CPUs. So the net increased to 70 kilograms. What was it before?
We don't know.
Okay.
Also, I think everything aspirationally was like 55. And so a
then
lot of the numbers we saw is like, this is what everyone wants to do. We don't really know what the Tesla bot is. We know that the Gen 2 reduced the weight like 10%.
Right.
And everyone assumed, oh, it was 50 or 55 because that's what the website said. It's like, wait a minute, what's on that website is like aspirational. It wasn't the real thing.
Yeah.
And it also said this, the speed is supposed to be 5 miles per hour on the, and we know the Tesla bot's going nowhere near 5 miles.
Right.
So we don't know exactly. Now I'm a little bit surprised. The batteries, yes, the batteries are heavy. That there could have been easily several kilograms. Do you think the cameras weigh that much, John? Because I always think of them being pretty light. So that would be like a small amount. And the CPU, GPU, a little bit. I think most of it's in the battery.
Yeah. Well, and structurally, he said that they added, weight to the structure. So it's
the exoskeleton should have reduced it. So it brought the mass down, but then these other components brought it up.
Yeah. So
it's a big leap though, right? I mean, if you look at figure 1, it didn't, I mean, it was okay, but look at all the wires sticking out. It looked pretty heavy. When he say exoskeleton, this looks like an exoskeleton to me. What's the difference?
Oh no, this has bones.
Yeah.
So you get the bones that are giving you the structure, whereas an exoskeleton would be like an insect, where you get where it's really soft in the middle, and so you could say it's like a tubular structure. I mean, just imagine building a bot out of PVC pipe. Right. Okay.
Hey, why didn't you do that?
Yeah. And there actually are some industrial robot. Like if you look at the universal robot, which is a cobot, it almost looks like it's made out of those type of pipe sections. And it's made that way for a couple of reasons. One is a cylinder is very strong. So if you want robustness, you want something that is kind of cylindrical in design. It can be hollow, which means you can run all your services, all your harnessing and everything through that. So it's very easy to sneak that stuff through. It's just figuring out how to get it through the joints, but at least it's kind of hidden in there. And the other reason that you make these cylindrical is there's no sharp edges or anything like that to either snag things on or to injure people. So that's why a lot of cobots are designed that way. That almost looks like they're made out of PVC piping. And that is because that is the softest shape that you can come up with. Anything else is going to be hard and is going to cause more likely bruising. So that's definitely made out of bones. And because it's made out of bones, you'll see all the harnessing that's there. Basically, the thing is your arteries and everything are exposed on the outside.
Why did they start with that? Why didn't they start with the exoskeleton?
Much more.
Probably didn't think of that. They took the same approach everyone else is that we've got to build a bony structure. And I'll say the exoskeleton was not on my bingo card. I think, and then I'm like, of course, because Brett comes from an aviation background.
Right.
That's how you build aircraft.
In fact, he even said it's like building.
He even said that, which was like, of course,
Yeah. But I mean, when you look at this version, it's like comical compared to the new one.
Yes.
Like you don't think about it until you realize how. This is interesting because it's white. We don't know exactly. We assume the underlying it's powder coated aluminum, but we don't know for sure. But
is
anyway,
this an exoskeleton or not?
No.
I don't think so. It looks like it has bones
so that
inside.
Skin there, that's just like plastic molded parts that because we've seen the Tesla bot without its skin. So there was it running around where we saw everything else. And that's why it makes it's a little bit complicated to figure out how you do the harnessing. So we do see there's some exposed harnessing in some parts of the Tesla bot because it's very hard to get that internal. And the main reason it's hard is because you got to get around those joints.
Where I'm getting at is that Tesla looks like they're ahead by generation for the hands. We've explained that, but now
for the next generation,
do you think that the next gen Tesla bot is going to be exoskeleton, or is they're going to stay with this version? Because they're working on the third gen that's going to release. We don't know what that looks like.
I think they have to, because remember, Elon said they're moving everything that's inside the palm of the hand. So you get 6 actuators. They're probably going to at least 7 actuators now. They have to go into that forearm. But look at that forearm right now. You've got these 2 black actuators there, which are needed to move the wrist around.
Right.
Yep.
So that's a problem. So all the services are going to be moved back here. Now, all you've done is you've taken the fact that you are putting electricity in there to run those things. That now that you've got to run the cabling through there. And in Lex's podcast, he talked about the carpal tunnel that you have in there that you would run everything through. So it's pretty clear that they're going to have some internal conduit. And I would suspect a kind of exoskeleton, because otherwise, where do you find the space for all those actuators unless you want them bulging out like some sort of muscle group or something like that? And you don't really want that, because the whole idea of moving everything back is it keeps everything here very thin and very skinny so you can go in. So we can see that what Figures had to do is that they have a bulky palm here. We also see it looks like it's wearing like the biggest Rolex watch you can imagine on each hand around the elbow, around the wrist right there, to be able to accommodate that movement. But they did come up with what looks almost like a carpal tunnel to be able to do the cable management. So when you see how the hand's attached there, they do have something that's there that has like internal routing, because I don't see the cables.
It's
so the
very,
cables
it's
must
very
be, yeah. So that's elegant. So that's very
yeah,
nice what
yeah,
they did.
that's really nice. Yeah. So, but you know, we can hypothetically compare against Gen 3 Optimus, but Gen 2, you could make an argument that the arm and hand structure is more advanced here. I think that's
It is, because it has the extra knuckle already.
Yeah, but I just also mean just the whole thing, because you don't have those, because I think Tesla's probably going to have to get rid of those 2 exposed actuators, and that's going
yeah,
to
they're going to, I agree. They're going to, they're going to riff on the idea. They're going to still try to figure out how to do that without it being so exposed, and maybe making them a little bit lighter and tighter. That will be kind of combined with the whole idea of the hand.
Exactly.
So by getting that in there, they may find some way of being able to do it. It's also going to be interesting to see how they get the roll on that hand.
Yes.
So here,
yes,
it's a little hard to see, but you can
there's
see
a
the
joint
whole
up
lower
there.
arm unit is actually able to rotate.
Yep, right
Yeah,
there.
you can see right there how that whole lower arm, and that's typically how almost all of them work.
There's a spot right here where you can see.
And the Tesla bot does the same thing. You know, right just past the elbow, there's a spot that it articulates on. And see, for us, we have like these two bones in there that kind of twist around when we do that, and we don't rotate at one location. The whole thing deforms. You know, it's not a rigid body movement. It's a very flexible one, and that's what makes it really hard for animators. Is the fact
believe me, I know. You get the candy wrapper effect when you do.
But if you just model it as like a cone on top of another cone, you can kind of twist it around, but you see the seam that's around there, and that's what we see in these bots.
Yep. But anyway, you know, it it definitely is walking a lot faster. When we were watching that Figure 1 demo you had up, it was walking very slowly and awkward.
Yes, it's faster. I think it's about the same as Optimus. We'll have to sit there and do the analysis to count it. It's probably a little bit more than a mile per hour right now. And remember, we want to get to, I think, like 2.5 miles per hour or something like that for it to be really good for useful work. But it's standing up a little bit straighter. You see there, their knees are really, really bent. And part of that is that they have that heavy backpack.
Right.
And that heavy backpack kind of just threw the.
And it also had to lean like this to keep the center of gravity appropriate. So it's standing much straighter up now.
So now it's definitely more erect in the way it's standing, but it could do more on the foot movement. So the Tesla bot is starting to get a little bit of that toe off. That's still kind of plodding along. And we saw that, not in this one, but in the teaser, a pretty good close up of the foot. And that tells me it's like there's a lot of potential there in that foot design, because it looks like it's got compliance in there. It's got these places to be able to do the heel toe kind of roll off based on its shape. It looks like it might have some energy absorbing capabilities on there. And it definitely has the degrees of freedom that you need to be able to articulate and move everything. So I would suspect that's going to be coming a little bit sooner.
Right. Yep. Very true. And you know, the AI inference is not a joke, but again, they're able to leverage NVIDIA, which is important for them because they don't have Tesla's design manufacturing of of silicon, so that's important.
Yeah, so the foot that we just saw, that's not a flat plank. There's a lot of engineering that went into that foot. So they must be thinking of doing something. Now they've done it a little bit different. SETI Park put up some interesting patents yesterday, which are patents from Unitree on the lower leg design. I'm not sure how many of those patents will, can actually be enforced, because a lot of the designs and everything else they have in there, everyone else has been doing that. And when they talk about, those who are skilled in the art, that if something is like completely obvious, you just can't say, I'm going to throw a patent on that. Now, what they've done here in Figure is that, and Tesla Bot and the others do the same thing now at the ankles, is they have these basically 2 connecting rods that allow you to get the pitch of the foot and to also get the roll back and forth that way. Figure just has a single one for being able to do it. They have a single connecting rod, which does the primary movement that you want to do on the foot, and that is to have it go up and down. Right now, it seems like they're only using it to make sure the foot stays level as the knee moves. So it's basically countering the angle at the knee and the hip is giving to keep that foot level. But there's no reason why you couldn't also use it to give you just that little bit of extra roll and toe off that you have. And it looks like they have a degree of freedom this way to keep the foot level when it comes down the floor. Now, you will need that a little bit when the hips widen out, you know, when it was trying to do that turn, because when you do that, your foot is going to be doing this and you have to counter that to make sure it stays flat in the floor. Right. So they have something like that. The question is whether that's a controlled degree of freedom, which I assume it is. It could also just be they have compliance in there. You put a big torsion spring in there, and then when your foot comes down off angle, it just naturally levels itself out and then kind of comes off. And it's, you know, and that would just be a design choice to say that it's such an unimportant kind of movement. Because think about we more or less just twist our foot there. We don't have a whole lot of strength to be able to make our foot go like that. You know, we get the strength to make it go up and down like that. But this thing, it's more or less, when it starts to do this, it's called a sprained ankle. That's about it. So it could be that you just go ahead and just put the compliance in there to allow that and only care about that. And that what that means is that you get rid of an actuator and everything else. But if you look at that foot, it looks like they could potentially cram a little one in there just to at least make the adjustment so that when the foot comes down, it comes down level.
Yep.
So when Elon was interviewed by Lex Friedman, he said that 50% of the engineering is actually the hands.
That's what it was. I was trying to remember the percentage, but he said it was a large percentage.
Is that a surprise?
No.
Yes.
No. Look at he did that. Lex put out that homunculus of the person, and the hands are huge on that.
The hands are huge, and that basically shows the amount, I guess, of number of nerves on the different parts of the body
and motor control. Yeah.
Yes. Yeah. For motor control, something like that. So what that does is shows the amount of different parts of your body that your brain is concerned with. And our brains co-evolved with our hands. Right. So, you know, that's this big argument of why embodied AI is so important, is because as something happened with nature, we accidentally had this opposing thumb that just evolved for some reason. Once that opposing thumb came in there, we started to be able to manufacture and play with tools. And then that just caused our brains to say, hey, you know, we can do some pretty cool things with it. And then our hands got more dexterous. Our brains were then able to accommodate for it. So it's very clear that both of those things came through together. Now, there's some big design changes that Tesla has decided to do with the hand that came out of Lex's podcast. And if you go back, and again, in that, Elon talks a lot about his mantra, the 5 principles that he kind of goes through and how he's got it wrong. He's learned the hard way about it. And if you look at the Isaacson book, when the Optimus team got together and they started looking at the hand, there was a raging argument over the number of fingers to have. You know, it's like, oh, we only need 3 fingers and stuff like that. And then they weren't sure where to go for. And they eventually decided to go to 5. And then they're thinking about, okay, but remember what Elon wants, you know, best part is no part. So that was like part of the reason, like, let's get rid of the fingers because the best part is no part. It's like, well, we have to have them, but at least make all the fingers the same length. And if you make them all the same length, it's like, you know, the best skew is no skew. So doing that will reduce costs, make it easier to put together. And they made a couple of design choices to get the arc in there of the fingertips just by doing the offset. But now as they've done it, and Elon talks about, it's like you need to take enough parts out that you have to start putting them in.
Yep. And
one of the things that the design team was, when they started to actuate it, they said, oh my God, we got to figure out where the position of this thing is. How do we control the thing? And they were thinking, we got to have all these different sensors and stuff like that. But then it was decided, no, take the sensors out. Let's simplify it as much as possible. Let's use back EMF, see how far we can get. They did that, and they decided, oh, we need to put sensors in the tips. Figure went the other way. They already put it in there, and they said, we're saying you need to take it out. Now, it may depend upon the application that they're going in. If you want to be able to count change in your hands, like James Dalma talks about, you need to have pressure sensors. If you're just picking up sheet metal to drop them into something, maybe you don't. It may be very easy. We'll see what it's like when you try to pick up stacked pieces of sheet metal, whether you want that fingertip kind of pressure sensor, stuff like that. Like, oh, I can feel the edge now, and now I know I can pull it up, as opposed to some other method. So we'll find out. But then Elon goes on talking about the importance of the pinky and everything else. It looks like all the fingers are going to be different lengths.
Yep.
Because he talked about that. So they went from, we're trying to simplify the hand, to realizing, my God, we've got to make it almost as complex as the human hand.
Right.
And then the idea that he mentions for sure that he said, we're designing, a 22-degree freedom arm.
Right.
And I thought it was a slip of the tongue, and it was like, no, it wasn't. And then he doubled down. He says, basically it's a whole new lower arm unit. Makes 100% sense that you would want to do that, because we don't realize that when you decouple it. So allow me here, Herbert, a second of talking about, how we solve big problems as engineers. We take the problems and we break them down into small, digestible chunks that we know how to solve. So the way we've always solved the problems in robotics is like, we've got a robotic arm that we're trying to figure out to move someplace, and we've got some sort of end of arm and tooling that we put on there, which is usually very rigid. And the first thing we do is say, what's the configuration of the end of arm tooling? And what's the relationship of like my fingertip? I want my fingertip to touch my nose right now. What's the relationship between that and my wrist? Now, if I know how I want my fingertip to be attached to my nose or wherever it's going, I now can predict where the center of my wrist needs to be. And I will then say, that's what you need to do. Get the wrist to there, and that's where your fingertip's going to be. You separate the problem out. So what would we be doing when we do it with a humanoid bot? We'd say, okay, I want to do something with my hand. What's the gesture your hand's going to be in? Figure it out. Is your fingertip going to be like this when you touch your nose, or it's going to be like that? So you kind of go through that whole thing and decide that I want my fingertip to be like that when I go and touch my nose. Now, okay, solve the problem with the arm to kind of get yourself to there. But maybe it turns out when I get myself there, I've got my wrist in a position that it's like, it's uncomfortable. Okay. How do I solve the problem of it being uncomfortable? Well, maybe I change the orientation of my finger around there. So what's going on is that you make some assumption about, this is what my hand's going to do this particular task, and now solve the arm with it. And you get there and you find out that you're making it difficult on your arm. Maybe you could move your elbow around, stuff like that. Let's not decouple these problems when suddenly you find out that, I'm going to have to change what's going on with my hand. I want to make it a single solution. So when you integrate the whole thing, and this is really hard to do heuristically. All right. It's not one of the, that's why
this is why we have neural networks.
That's why you break, because heuristically it's easy to break it down. When you try to make it an integrated problem to say, what is the smoothest, best direct way to get that finger to come up to Scott's nose where my hand and everything else feels comfortable and natural? It's like, it's whatever the best gesture is that feels right. It's not that I ahead of time say my fingers are going to be angled like this and that's going to work. See, if I want to get that tip on there, see, that's going to be uncomfortable to be able to get that. So you integrate all these things together rather than decoupling that. And that's really what's the next big breakthrough is going to be when we see the Gen 3, is that full integration. And that full integration from a software standpoint, it's not ending at the elbow. It's going like all the way up. Now, whether they're designing everything else all the way up here to the elbow is another question. I really, really hope they are thinking of changing that a little bit. But the fact that they're changing that lower arm means the whole approach to how you solve motion is radically changing. And it's very important that it doesn't stop at the shoulder either. It starts to include torso movement.
Yeah, I was going to ask you that.
Everything else.
If they change the arm, they're going to change everything, right?
Oh yeah. Because you want to. Again, we make this problem of that. We figure out where the arm's going to be. Now, what does my torso have to do to get that, based on the placement of my feet, and my feet are on the ground, and my feet have to move around? Because you'll notice whenever you do the reaching, your whole body is part of the movement.
All the limbs will now become the bones or the thighs are going to also be part of the same ligaments and muscles.
And that's why a lot of these bots look stiff when they're moving, is because they're breaking it down as a single thing like that. And then when they solve one problem, they try to fit it into the other, which means they get a kind of a clunky solution to get it together, as opposed to find the most natural, smoothest one, which we have learned, over our lifetime, is that when we do something, we don't move our arm. Our whole body is part of it. The hip motion is there. It's very subtle. It's very nuanced, but it's very important being able to do it in a very smooth manner, as opposed to and after the fact.
Yeah, this is what the expectation, and I think right now, my guess, because I'm not working for these companies, but my guess is that they have a walking algorithm, not an algorithm, but a neural network that does the walking. They then have one that's arm manipulation and finger manipulation. What you want is much more like full self-driving, but the problem, of course, is the control out is much more complex than a car, which is end to end. You want it to control
Mhm.
everything. So it's controlling from your toe to your fingertip as you do
Yep.
any motion. Sometimes
Everything.
if I just do this, no big deal. But even that, my body's reacting to that
It's
just a little
reacting.
bit. Yeah.
It
So,
has to.
it's always doing that. So you're not going to get that weird clunky motion where it's like, it looks like a piece of the body is not attached to the rest of the body.
And it's not properly
that's,
coordinated
yeah.
as far as the movement. So
Yeah.
a lot of times, especially when you're reaching up in a cupboard or something like that,
Yeah.
you're not keeping your torso stiff. Your
Right. You
torso
actually move towards
is
it.
going
Yeah.
in there to get that
Mhm.
extra reach. But when I'm doing that, I'm throwing my center of gravity off, which means my hips and everything, they have to compensate for that. And it might even mean I have to spread my leg out a little bit
Mhm.
to
Right.
give me that additional balance.
Or press on your toe to push
Right,
backwards
right.
to give a
And
little
that's not
extra
something I want to
force.
discover that, like, as I'm doing this, it's like, oh, I'm losing my balance.
Yeah.
It's like, I already know intuitively when I start to do it, my legs just already bounce out like that with it because they just know that, oh, I've seen this movie before. And
Right.
sometimes you fall over when you don't put your foot out. So now I know, put your foot out. And that's what a good training policy is
How
going to do.
important
Is
is
that you
that?
get enough of that information, you know how it works.
How important is that if
I have
Okay,
to I
yeah.
have to get to work. So yeah, I got to do
Thank
my
you,
day
John.
job. But yes, thank you so much. Really good conversation. And yeah, keep watching, everybody. So cheers, folks. Bye-bye.
Thanks.
Bye, John.
How important is that if these bots can now do useful work in a factory? How important is everything you just said?
Okay, that will be important in the end to speed and also energy consumption. So you're trying to optimize a lot of things. And the reason our bodies do what they do is because we're lazy. In nature has evolved that they want us to be as lazy as possible because we're constantly in a state of an energy crisis. As animals are. They're constantly trying to find calories and stuff like that. So whatever you can do to reduce the number of calories that are needed means you're going to come up with more efficient ways of doing things. So our walking strides, everything else is designed to be able to actually make sure we do it in the most efficient way possible.
Yeah.
So that's going to be important. It also helps from wear and tear. I mean, the other thing that nature is concerned of is injuries. And you don't want to get yourself in these configurations that you're putting too much strain on your lower back or something like that. Of course, some of us learn the hard way, but in the end, you want everything to be done in such a way that you get fluidity in there. The other is that if you use everything right, I mean, if you look at the Olympic Games and you look at some of these crazy things these athletes are doing, the reason they're able to do it is because they have found an extremely efficient way to do it. It's very hard for us because we don't see the little nuances.
Right.
But all those things are in there because it's what makes it look easy. And we want the robots to do things that look easy. And if it starts looking hard, you can say, okay, it's not being very efficient as a mechanism. There must be a better way of being able to do it. That why am I kind of fighting forces when I could be using a lot of these things together? So it'll help speed, it'll help dexterity. It's going to be interesting to see what they have to do going forward. So this is interesting to see. I would say what we've seen is not much different than we saw about a month ago when Figure 1 was retired. So 6 weeks ago, we know that they were shipping a small fleet to a client and the box was empty, right? The shipping container was empty, which was a hint to me. It's like, why aren't they showing the bot in there? Because they're not shipping Figure 1. They're shipping Figure 2. They just didn't want that to be revealed. And so the small fleet, and you see that it's 5 bots that are there. And then I think about a week later, we saw pretty much the same demonstration of loading the sheet metal into the fixtures in the pilot area, not actually in the production floor, but where they go ahead and do the testing of these things. And it was said, okay, Figure 1 is now retired, which is like, okay, that means there's definitely a Figure 2. But no one made it like a big deal about it. It's like, well, the reveal is going to be coming at some point. So now they've got enough training data for Figure 2, because remember, Figure 2 is a different bot. It's not the same as the first one. So it may not be that easy just to take everything you learned from the first one and bring it on over, especially if you're going end to end. It's like, everything is servo controls, everything a little bit different. So you're going to get that trained up. And they've now are confident enough to go from the pilot area down to the floor. Now they're probably doing that in the off shifts. I'm not sure whether BMW is running like 3 full shifts or 2 shifts or something like that. So they're probably going in the off hours, because it's only able to load basically 1 piece of sheet metal at a time. Because if you go back over that frame, it's empty. Where's the next part? Where's that part coming from? There's no conveyor system that's feeding it. What's happening is that those orange boxes is some human runs over there, pulls a part out, and puts it in there and says, okay, here's the next one. Here's the next one. And if you look at that, so well, wait a minute, that's like a turtles all the way down kind of situation here. It's like the idea is to get the humans out of the loop and not to keep them in there. So the next step is going to be able to figure out how to pull it out of the dunnage. And that's what I want to be able to see. But it's pretty clear it was time to reveal figure 2 to get an idea of what it looks like. They've definitely made a lot of design improvements and changes to it. As you can see here, I've talked about, again, I like the way the shoulder is mounted. I'm impressed that they're able to get 2.3 kilowatt hours of battery into there. It seems to be a very robust design. And again, let's go back. If we go a little bit forward in the video, I want you to see why you want this robot to be robust.
Which part?
If you go back to the end, when we get to, okay, right about there, back off a little bit. I think it's like one of the end frames. After we're all done, we're going to take a look at the dunnage in there. So again, this is definitely on the production line. And again, I mean, these frames are set up to make it easy to pick. These are very easy, low-hanging fruit as far as, accuracy. You don't have to be super accurate when you drop those things in there. They are designed to just kind of drop into where they're supposed to. And when those fixtures close down, the fixtures make sure they get into their final locked position with the accuracy that you need. Okay, so pause right there and look at the dunnage.
What's a dunnage?
That dunnage is banged up.
What's a dunnage?
You see? I mean, look,
so
you look at the orange crates that are there.
Yeah. Yeah.
And look how many times like the forklifts banged into those things. Okay. That's what it's like being on the shop floor. Things get dropped, things get accidentally banged into. No matter how hard you try to make sure things don't happen, they do happen. So, the expectation is these bots are going to be in this kind of physical environment where a lot of things are being thrown around. They're going to fall, they're going to trip, they're going to have issues like that. So you need to design these things to be able to fall and to be a little bit stronger. The 70 kilograms tells me it's really going to be designed for that. It's going to be a question of whether there's ever going to be sort of standards that are going to say, is it safe to be around a bot that's 70 kilograms? Most humans weigh around that. So that or more. And because of the rounded design, it may not be that bad if it accidentally falls on a person, but still, if one person falls on another person, it still hurts as well.
Sounds good. Yeah. So what we did was we saw the new version of Figure, and it's impressive, right? You got more cameras, you get the more battery. That's the one that impressed me the most. 20 hours of useful work.
Yes.
You got the onboard vision language model and the speech to speech. They didn't show any benefit or increase in processing there. I think normal.
The onboard VLM is probably just to make sure it's able to execute its task. The speech-to-speech reasoning is not something it has to do during its task. That's just like the interface when you need to tell it to do something. But once it gets going, you don't need the speech-to-speech running the whole time.
But the big difference is the exoskeleton structure, which they didn't have before. And then, of course, all the wiring is now integrated. And then they did have an improvement in the hands. Although, if Elon is correct, this is not enough. They're going to need to improve this hands just a little bit more. A lot more. Yes, they're a generation behind of what Tesla seems to be thinking that you need to have.
Right.
It's only 16 degrees of freedom. Tesla's already headed to 22, but very beautiful, gorgeous.
Right. Now the 22, and again, I just want to underscore this point, is that it's really a 19-degree freedom hand with the wrist in there, which gives you the 22. Which was my hint that it's like they're thinking of the hand and the lower arm as an integrated unit. And that's definitely what Elon pointed out in his podcast with Lex, is that's how they think of it. Yeah. Is that it's not a 16-degree of freedom or 19-degree of freedom hand on the end of the arm. It really is something that's integrated. So in this case, that means there's about 3 degrees of freedom difference between the two. So because this is a 16, and a lot of that just comes to this movement right here. Gotcha.
Yep. Awesome. Okay. Thank you so much, Scott. Appreciate you jumping on board. This is the second generation of Figure robot. Thanks, everybody. Talk soon. Bye-bye.